Welcome back to the deep dive. We have a stack of research on the desk today that I am, well, genuinely excited about.
Oh, yeah.
Yeah. Usually when we talk cybersecurity, we're talking about the abstract stuff, you know, invisible data in the cloud, protecting your email password.
Or things you can't touch.
Yes.
Things that exist on a server somewhere in a basement.
Exactly. But today, we're going to a place where the digital world crashes, and I mean sometimes quite literally, into the physical world. We are talking about operational technology. OT security.
This is where the rubber meets the road. Or, I suppose more accurately, where the code meets the conveyor belt.
It's a fascinating area because all the rules we take for granted in IT, they completely flip upside down here.
And to guide us through this looking glass world, we are analyzing the study materials for a very specific certification. It's the Fortinet NSE6, that's our 7.6 exam.
Part of their FCSS, or Secure Networking Track. Now, I know exam prep sounds a little dry, but as I was going through these questions, I realized this isn't just a test. It's essentially a field guide for how to keep modern infrastructure from falling apart.
That's the best way to view it. This exam specifically targets the architect role. So it's not just asking which button do I click, it's asking how do you design a fortress around a nuclear plant, a car factory, or, a water treatment facility.
Okay, before we get into the architecture, give us the lay of the land. If someone is listening to this in the parking lot of a testing center right now, what are they walking into?
It's a sprint. You have exactly 65 minutes.
That is tight.
It is very tight. You're looking at roughly 35 to 40 questions. The format is standard, multiple choice, multiple select. But don't let that fool you. The questions are designed to trip you up if you answer like an IT admin.
What do you mean?
If you go in there thinking about confidentiality and data privacy as your top priorities, you will fail.
That is a perfect transition to our first big idea. In the IT world, data is king. If I hack a bank, I want the data, right? I want the numbers.
Absolutely. But in OT, the priority hierarchy is completely different.
How so?
In OT, availability and safety are king. If an email server goes down for 10 minutes, people get annoyed.
They can't send a memo.
Exactly. If the cooling system in a chemical plant goes down for 10 minutes, you might have an environmental disaster. You might have an explosion.
Which brings us to this do no harm principle. This was the biggest aha moment for me in the source material. In IT, if I want to know what's on my network, I scan it.
Standard procedure. You run a tool like Nmap, you ping everything. You need visibility.
But looking at question 5 of the practice exam, if you do that in an industrial setting, you are in big trouble.
You're in massive trouble. The question asks about the major technical risk of performing an active scan on legacy industrial controllers. And the answer isn't that you'll, fill up the hard drive. It's C. It could cause the controller to malfunction or stop the process entirely.
I want to dig into that because it seems so counterintuitive. We're talking about giant steel machines, right? Turbines, furnaces. You're telling me a digital hello can break them.
You have to look at the history. A lot of these PLCs, these programmable logic controllers, they were designed 20, maybe 30 years ago.
Before the internet was really a thing.
Right. These devices were built to do one job: turn a valve, read a temperature, spin a turbine. Their networking stack is incredibly primitive. They aren't multitaskers.
So when a modern scanning tool hits them,
it's just a flood. The tool sends thousands of packets a second asking what port is open, what version are you running. To a legacy PLC, that's like a denial of service attack. It gets overwhelmed processing the questions and stops doing its main job.
It reminds me of like a master watchmaker. He's focusing on placing a tiny gear and someone runs in and screams, "What's your name?" right in his ear.
That is the perfect visual. He drops the gear, the watch stops. And in a factory, dropping the gear means the assembly line halts, and that costs thousands of dollars a minute. Or worse, a safety mechanism fails.
So the exam emphasizes this heavily. Active scanning is dangerous. You listen, you don't poke.
Exactly. You use passive methods.
Okay, so if these devices are so fragile we can't even scan them, I'm guessing we can't update them either. You can't just run a Windows update on a Firmus controller from 1998.
You definitely can't. You often can't patch them. The vendor might be out of business, but, and here's the catching, those devices still have vulnerabilities. They have bugs that hackers know about.
That sounds like an absolute nightmare. You have a vulnerable machine, but you can't touch it to fix it because touching it might break it.
And that leads us right to question 1 in the material, the concept of virtual patching.
I love this term. It sounds like something out of a video game.
It's actually a very practical solution to this exact problem. The question asks for the fundamental objective of using virtual patching on a FortiGate. The answer is C, to use security signatures to block attacks targeting unpatched vulnerabilities.
Okay, explain how that works mechanically. If I'm not patching the machine, how is it protected?
Think of it like a shield, or better yet, a quarantine bubble. If you have a person, the machine, with a compromised immune system, you can't give them a vaccine because it might make them sick. So what do? You put them in a bubble.
Okay, that makes sense.
In networking, you place a firewall, the FortiGate, directly in front of the vulnerable machine. The firewall has an intrusion prevention system, an IPS. It knows what the exploit looks like.
So the firewall stands guard.
Exactly. When a hacker sends a malicious packet that would normally exploit that unpatched hole, the firewall sees it coming and just blocks it on a wire.
So the attack never actually touches the legacy machine.
Precisely. The machine remains vulnerable, but to the outside world, it is shielded. You have virtually patched it without risking the downtime of a reboot.
That is incredibly clever. It buys you time until you can replace the hardware during a scheduled shutdown, which might only happen, once a year?
Exactly. Lets you operate securely in an insecure environment.
Now, speaking of shields, let's talk about physical constraints. We've established software scanning is dangerous, but sometimes you need a wall that is stronger than software. I saw this concept in question 3 called a data diode.
Yes, this is one of my favorite controls because it relies on physics, not just code.
I know a diode in electronics lets electricity flow one way. Is a data diode the same thing for information?
Precisely. The question asks about the primary physical security constraint of a hardware-based data diode, and the answer is A. It strictly forces data to travel in only one physical direction.
One physical direction. So this isn't just a software setting where I check a box that says read only.
No, and that is the critical distinction. Software can be hacked. Configurations can be changed. A true data diode often uses fiber optics. Inside the box, you have a sender on one side and a receiver on the other. But, and here's the key, there's physically no sender on the receiving side.
So even if a hacker completely took over the receiving network, they literally cannot send a single bit of data back.
Correct.
Yeah.
There is no path. It's like shouting across a canyon. You can hear me, but you can't throw anything back.
Where do you actually use something that extreme? Because the whole internet is built on two-way communication.
Critical infrastructure, nuclear power plants, water treatment facilities. You want to send data out to say, the reactor temperature is normal. But you never, ever want a signal coming in that can say, shut down the cooling pumps.
It's the ultimate keep out sign. It isn't please don't enter. It is there is no door.
It's very effective, but it needs careful planning.
That brings us to the language these machines speak. Question 4 brings up the B8net protocol.
B8net. If you work in OT, you see this everywhere.
The question asks where this protocol is most commonly used. And the options were things like high-speed car assembly, but the answer was B, building automation and climate control systems.
Right. B8net stands for Building Automation and Control Networks.
So we're not talking about robots building cars here. We're talking about the office building we're in.
We are talking about the environment you're sitting in right now. The HVAC system keeping the studio cool, the automated lighting, the badge access control on the doors.
Why does a security architect need to know about the air conditioning protocol? It feels like facilities management, not cybersecurity.
Because the environment is part of the security. Imagine a data center. If I can hack the BACnet system and turn off the cooling, the servers overheat and shut down.
Oh, wow. You've caused a denial of service without ever touching the servers.
Exactly. Or simpler, just unlocking all the doors. Physical security and cybersecurity merge here. If I see BACnet traffic, I immediately know what I'm dealing with.
It really reinforces that OT is everywhere. It's in the ceiling tiles above us.
It is, and protecting it is just as critical.
So we have fragile machines, one-way streets, special languages. Let's zoom out to the architecture. How do you organize all this? These factories have to connect to the corporate office, right?
Yes, and that connection, that bridge between IT and OT is historically the most dangerous part of the whole design.
And that's where question 10 comes in, asking about the purpose of a DMZ layer.
The demilitarized zone.
It sounds like a war movie.
In cybersecurity, it's an appropriate term. The answer here is D. To provide a controlled isolation zone for shared services and data transfer.
So it's a buffer. An airlock.
Exactly. You have the corporate network on one side that's full of danger, people checking email, clicking phishing links. It's dirty by OT standards. Then on the other side, you have the clean industrial network where the machines live.
And you never want the dirty network touching the clean network.
Never. A ransomware infection from a marketing email could spread straight to the factory floor. The DMZ sits in the middle. If I need to pass a file, I put it in a server in the DMZ, close the door, and then the OT side opens its door and picks it up.
So there's never a direct line of sight. It breaks the attack path.
That's the goal. A hacker hits the DMZ wall. They can't just pivot straight to the turbine controls.
But what if they do get past it? Or a technician walks in with an infected laptop and plugs right in?
That is the modern challenge. In the old days, we relied on fences. Today, we need zero trust.
Question 2. Zero Trust Network Access, or ZTNA. Zero Trust sounds a bit cynical.
It is cynical.
Yeah.
But it's the healthiest attitude. The question asks for the mandatory requirement for access in a zero-trust architecture.
And the answer wasn't be a permanent employee or anything like that.
No. The answer is D. Continuous verification of the device identity and its security status.
The key word is continuous, right? How is that different from a VPN?
A VPN is like a castle moat. Once you're across the drawbridge, you're inside. You're trusted, you can roam around. If you get a virus 10 minutes later, the network doesn't know.
Okay, I see.
With zero trust, there is no drawbridge. The system checks you constantly. Every time you try to open a file, it checks again. Are you still who you say you are? Is your antivirus running?
It's like a bouncer who doesn't just check your ID at the door, but follows you around checking it every 5 minutes.
A little intrusive for a club, maybe, but absolutely necessary when you're protecting a power grid. It moves from where you are to who you are and how healthy your device is.
Which is critical for OT. So, okay, we've got the architecture, DMZ at the perimeter, zero trust for the users. But there's another challenge. The sheer volume of stuff. A refinery has thousands of sensors, pumps, controllers.
It's chaos. Unlike IT, where you have 500 identical laptops, in OT you have hundreds of different devices from different manufacturers, different vintages.
And that's where question 6 comes in, about asset tags in the Fortinet security fabric. It sounds basic, like stickers on equipment.
Digital stickers. The question asks their main purpose. The answer is D. To group devices logically for simplified security policy management.
Why is grouping so important? Can't I just use IP addresses?
You can, but it's a trap. Say you have 50 pumps. If you write a rule using IPs, you have to type in 50 addresses. And if you type one wrong, you just broke a pump or left a hole open.
Ah, I see. And if a pump gets replaced, it gets a new IP and the rule breaks.
Exactly. With tags, you just tag all 50 devices as pumps. Then you write one rule, allow pumps to talk to controller. You add a new pump, you just tag it, and it automatically inherits the rules.
That makes so much sense. It just reduces human error.
Drastically.
Speaking of understanding what's happening, a standard antivirus isn't going to help if someone tries to overpressurize a pipe.
Right. You need intelligence that speaks the language. Question 8 highlights the FortiGuard OT security service. It provides parallelized signatures for industrial protocol commands and vulnerabilities.
Protocol commands is the key phrase there. It's not looking for malware files. It's looking for bad commands.
Exactly. Imagine a stop command sent to a safety system. The command itself is valid code, but if it's sent at 3:00 a.m. from an unauthorized IP address, it is an attack.
So it's not malware, it's sabotage using the machine's own language.
Precisely. The OT service understands Modbus and all these other industrial protocols. It can see a valid command being used maliciously. A standard firewall would just see data and let it through.
That's the difference between a spell checker and a fact checker.
That's a brilliant way to put it.
But when the alarm does go off, because eventually something will happen, speed is everything.
Speed is life. A breach left alone for an hour in OT could mean physical damage.
And question 7 talks about Fortisora playbooks. What is a playbook?
It's automation. The answer is A. To automate a sequence of response actions for specific security alerts.
So instead of a human analyst seeing a red light, spilling their coffee, and trying to figure out what to do,
the system does it for them.
Yeah.
Instantly. The alarm trips and the playbook executes. Block the port, isolate the workstation, send an email to the plant manager. All in milliseconds.
And that consistency must matter.
Huge. Human panic is a real security vulnerability. Playbooks remove the panic.
But let's say the worst happens. The incident is contained. What comes next? Question 9 takes us to the aftermath.
The forensic analysis.
I thought this one was interesting. The question asked for the primary goal, and one of the wrong options was to find a reason to fire the operator.
Yeah, the blame game. In safety-critical industries, a culture of blame is dangerous. If people are afraid of being fired, they hide their mistakes, they delete logs.
So the goal isn't to pin it on someone.
No. The correct answer is C, to determine the root cause of the breach and the path taken by the attacker.
Why is root cause so important?
Because if you don't find it, it will happen again. If you just reimage the PC but don't figure out how they got in, was it a weak password? A phishing email?
Yeah.
You're just waiting for the sequel.
And in OT, the sequel is usually worse.
Always. You have to map that attack path. Did they come through the HVAC system? A vendor VPN. Once you know the path, you can close it. It's about learning, not punishing.
To everyone listening, stay curious, stay secure, and keep an eye on those invisible systems running your life. We will catch you on the next deep dive.
Goodbye, everyone.